Hello, this is Teacher Todd, and I'll be presenting Chapter 5 of Network Security Essentials by William Stallings. This chapter begins our discussion of network security, focusing on two key topics, network access control and cloud security. We begin with an overview of network access control systems, summarizing the principal elements and techniques involved in such a system. Next, we discuss the Extensible Authentication Protocol and IEEE 802.1x, two widely implemented standards that are the foundations of many network access control systems. The remainder of the chapter deals with cloud security. We begin with an overview of cloud computing and follow this with a discussion of cloud security issues. Network Access Control, NAC, is an umbrella term for managing access to a network. NAC authenticates users logging into the network and determines what data they can access and actions they can perform. NAC also examines the health of the user's computer or mobile device, the endpoints. NAC systems deal with three categories of components. Access Requester, AR. The AR is the node that is attempting to access the network and may be any device that is managed by the NAC system, including workstations, servers, printers, cameras, and other IP-enabled devices. ARs are also referred to as supplicants, or simply clients. Policy Server. Based on the AR's posture and an enterprise's defined policy, the policy server determines what access should be granted. The policy server often relies on backend systems, including antivirus, patch management, or user directory, to help determine the host's condition. Network Access Server, NAS. The NAS functions as an access control point for users in remote locations connecting to an enterprise's internal network. Also called a media gateway, a remote access server, RAS, or a policy server, an NAS may include its own authentication services or rely on a separate authentication service from the policy server. This figure is a generic network access diagram. A variety of different ARs seek access to an enterprise network by applying to some of the NAS. The first step is generally to authenticate the AR. Authentication typically involves some sort of secure protocol and the use of cryptographic keys. Authentication may be performed by the NAS, or the NAS may mediate the authentication process. In the latter case, authentication takes place between the supplicant and an authentication server that is part of the policy server or that is accessed by the policy server. The authentication process serves a number of purposes. It verifies a supplicant's claimed identity, which enables the policy server to determine what access privileges, if any, the AR may have. The authentication exchange may result in the establishment of session keys to enable future secure communication between the supplicant and the resources on the enterprise network. Typically, the policy server or a supporting server will perform checks on the AR to determine if it should be permitted interactive remote access connectivity. These checks, sometimes called health, suitability, screening, or assessment checks, require software on the user's system to verify compliance with certain requirements from the organization's secure configuration baseline. For example, the user's anti-malware software must be up to date, the operating system must be fully patched, and the remote computer must be owned and controlled by the organization. These checks should be performed before granting the AR access to the enterprise network. Based on the results of these checks, the organization can determine whether the remote computer should be permitted to use interactive remote access. If the user has acceptable authorization credentials, but the remote computer does not pass the health check, the user and remote computer should be denied network access or have limited access to a quarantine network. so that authorized personnel can fix the security deficiencies. The figure indicates that the quarantine portion of the enterprise network consists of the policy server and related AR suitability servers. There may be application servers that do not require the normal security threshold be met. Once an AR has been authenticated and cleared for a certain level of access to the enterprise network, the NAS can enable the AR to interact with resources in the enterprise network. The NAS may mediate every exchange to enforce a security policy for this AR, or may use other methods to limit the privileges of the AR. Network access enforcement methods. Enforcement methods are the actions that are applied to ARs to regulate access to the enterprise network. Many vendors support multiple enforcement methods simultaneously, allowing the customer to tailor the configuration by using one or a combination of methods. The following are common NAC enforcement methods. IEEE 802.1x. This is a link layer protocol that enforces authorization before a port is assigned an IP address. IEEE 802.1x makes use of the extensible authentication protocol for the authentication process. Sections 5.2 and 5.3 cover the extensible authentication protocol and IEEE 802.1x, respectively. Virtual local area networks, VLANs. In this approach, the enterprise network, consisting of an interconnected set of LANs, is segmented logically into a number of virtual LANs. The NAC system decides to which of the network's VLANs it will direct an AR, based on whether the device needs security remediation, internet access only, or some level of network access to enterprise resources. VLANs can be created dynamically, and VLAN membership, or both enterprise service and ARs, may overlap. That is, an enterprise server or an AR may belong to more than one VLAN. Firewall. A firewall provides a form of NAC by allowing or denying network traffic between an enterprise host and an external user. Firewalls are discussed in Chapter 12. DHCP management. The Dynamic Host Configuration Protocol, DHCP, is an internet protocol that enables dynamic allocation of IP addresses to hosts. A DHCP server intercepts DHCP requests and assigns IP addresses instead. Thus, NAC enforcement occurs at the IP layer based on subnet and IP assignment. A DHCP server is easy to install and configure, but is subject to various forms of IP spoofing, providing limited security. There are a number of other enforcement methods available from vendors. The ones in the preceding list are perhaps the most common, and IEEE 802.1x is by far the most commonly implemented solution. The Extensible Authentication Protocol, EAP, defined in RFC 3748, acts as a framework for network access and authentication protocols. EAP provides a set of protocol messages that can encapsulate various authentication methods to be used between a client and an authentication server. EAP can operate over a variety of network and link level facilities, including point-to-point links, LANs, and other networks, and can accommodate the authentication needs of various networks and links. The figure illustrates the protocol layers that form the context for EAP. EAP supports multiple authentication methods. This is what is meant by referring to EAP as extensible. EAP provides a generic transport service for the exchange of authentication information between a client system and an authentication server. The basic EAP transport service is extended by using a specific authentication protocol or method that is installed in both the EAP client and the authentication server. Numerous methods have been defined to work over EAP. The following are commonly supported EAP methods: EAP-TLS, EAP Transport Layer Security, EAP-TLS, which is RFC 5216, defines how the TLS protocol described in Chapter 6 can be encapsulated in EAP messages. EAP-TLS uses the handshake protocol in TLS, not its encryption method. Client and server authenticate each other using digital certificates. Client generates a pre-master secret key by encrypting a random number with the server's public key and sends it to the server. Both client and server use the pre-master to generate the same secret key. EAP-TTLS. EAP tunneled TLS. EAP-TTLS is like EAP-TLS, except only the server has a certificate to authenticate itself to the client first. As in EAP-TLS, a secure connection, the tunnel, is established with secret keys, but that connection is used to continue the authentication process by authenticating the client and possibly the server again using any EAP method or legacy method such as PAP, Password Authentication Protocol, and CHAP, Challenge Handshake Authentication Protocol. EAP TTLS is defined in RFC 5281. EAP GPSK, or EAP Generalized Pre-Shared Key. This is defined in RFC 5433, is an EAP method for mutual authentication and session key derivation using a pre-shared key, PSK. EAP GPSK specifies an EAP method based on pre-shared keys and employs secret key-based cryptographic algorithms. Hence, this method is efficient in terms of message flows and computational costs, but requires the existence of pre-shared keys between each peer and EAP server. The setup of these pairwise secret keys is part of the peer registration and thus must satisfy the system preconditions. It provides a protected communication channel when mutual authentication is successful for both parties to communicate over and is designed for authentication over insecure networks such as IEEE 802.11 Wi-Fi. EAP GPSK does not require any public key cryptography. The EAP method protocol exchange is done a minimum of 4 messages. EAP IKE v2. It is based on the Internet Key Exchange Protocol version 2, which is described in Chapter 9. It supports mutual authentication and session key establishment using a variety of methods. EAP TLS is defined in RFC 5106. This figure indicates a typical arrangement in which EAP is used. The following components are involved. EAP peer, client computer that is attempting to access a network. EAP authenticator, an access point or NAS that requires EAP authentication prior to granting access to a network. Authentication server, a server computer that negotiates the use of a specific EAP method with an EAP peer, validates the EAP peer's credentials, and authorizes access to the network. Typically, the authentication server is a remote authentication dial-in user service, RADIUS server. The authentication server functions as a back-end server that can authenticate peers as a service to a number of EAP authenticators. The EAP authenticator then makes the decision of whether to grant access. This is referred to as the EAP pass-through mode. Less commonly, the authenticator takes over the role of the EAP server. That is, only two parties are involved in the EAP execution. As a first step, a lower level protocol such as PPP, point-to-point protocol, or IEEE 802.1x is used to connect to the EAP authenticator. The software entity in the EAP peer that operates at this level is referred to as the supplicant. EAP messages containing the appropriate information for a chosen EAP method are then exchanged between the EAP peer and the authentication server. EAP messages may include the following fields. Code identifies the type of EAP message. The codes are request, response, success, and failure. Identifier used to match responses with requests. Length indicates the length in octets of the EAP message, including the code, identifier, length, and data fields. Data contains information related to authentication. Typically, the data field consists of a type subfield indicating the type of data carried and a type data field. The success and failure messages do not include a data field. The EAP authentication exchange proceeds as follows. After a lower level exchange that established the need for an EAP exchange, the authenticator sends a request to the peer to request an identity, and the peer sends a response with the identity information. This is followed by a sequence of requests by the authenticator and responses by the peer for the exchange of authentication information. The information exchanged and the number of request-response exchanges needed depend on the authentication method. The conversation continues until either 1, the authenticator determines that it cannot authenticate the peer and transmits an EAP failure, or 2, the authenticator determines that successful authentication has occurred and transmits an EAP success. This figure gives an example of an EAP exchange. Not shown in the figure is a message or signal sent from the EAP peer to the authenticator using some protocol other than EAP and requesting an EAP exchange to grant network access. One protocol used for this purpose is IEEE 802.1x, discussed in the next section. The first pair of EAP request and response messages is of type identity, in which the authenticator requests the peer's identity, and the peer returns its claimed identity in the response message. The response is passed through the authenticator to the authentication server. Subsequent EAP messages are exchanged between the peer and the authentication server. Upon receiving the identity response message from the peer, the server selects an EAP method and sends the first EAP message with a type field related to an authentication method. If the peer supports and accepts the selected EAP method, it replies with the corresponding response message of the same type. Otherwise, the peer sends a NAC and the EAP server either selects another EAP method or aborts the EAP execution with a failure message. The selected EAP method determines the number of request-response pairs. During the exchange, the appropriate authentication information, including key material, is exchanged. The exchange ends when the server determines that authentication has succeeded or that no further attempt can be made and authentication has failed. Terminology related to IEEE 802.1x. IEEE 802.1x port-based network access control was designed to provide access control functions for LANs. The table briefly defines key terms used in the IEEE 802.11 standard. The term supplicant, network access point, and authentication server correspond to the EAP terms peer, authenticator, and authentication server, respectively. Until the AS authenticates a supplement using an authentication protocol, the authenticator only passes control and authentication messages between the supplicant and the AS. The 802.1x control channel is unblocked, but the 802.11 data channel is blocked. Once a supplicant is authenticated and keys are provided, the authenticator can forward data from the supplicant, subject to a predefined access control limitations for the supplicant to the network. Under these circumstances, the data channel is unblocked. As indicated in the figure, 802.1x uses the concepts of controlled and uncontrolled ports. Ports are logical entities defined within the authenticator and referred to physical network connections. Each logical port is mapped to one of these two types of physical ports. An uncontrolled port allows the exchange of protocol data units between the supplicant and the AS regardless of the authentication state of the supplicant. A controlled port allows the exchange of PDUs between a supplicant and other systems on the network only if the current state of the supplicant authorizes such an exchange. The essential element defined in 802.1x is a protocol known as EAPOL, which is EAP over LAN. EAPOL operates at the network layers and makes use of an IEEE 802 LAN, such as Ethernet or Wi-Fi, at the link level. EAPOL enables a supplicant to communicate with an authenticator and supports the exchange of EAP packets for authentication. Common EAPOL frame types. The most common EAPOL packets are listed in the table. When the supplicant first connects to the LAN, it does not know the MAC address of the authenticator. Actually, it doesn't know whether there is an authenticator present at all. By sending an EAPOL start packet to a special group multicast address, which is reserved for IEEE 802.1x authenticators, a supplicant can determine whether an authenticator is present and let it know that the supplicant is ready. In many cases, the authenticator will already be notified that a new device has connected from some hardware notification. For example, a hub knows that a cable is plugged in before the device sends any data. In this case, the authenticator may preempt the start message with its own message. In either case, the authenticator sends an EAP request identity message encapsulated in an EAPOL-EAP packet. The EAPOL-EAP is the EAPOL frame type used for transporting EAP packets. The authenticator uses the EAP key packet to send cryptographic keys to the supplicant once it has decided to admit it to the network. The EAP logoff packet type indicates that the supplicant wishes to be disconnected from the network. The EAPOL packet format includes the following fields: protocol version, which is the version of the EAPOL. Packet type indicates start, EAP, key, logoff, etc. Packet body length. If the packet includes a body, this field indicates the body length. Packet body. The payload for this EAPOL packet. An example is an EAP packet. And the figure shows an example of an exchange using EAPOL. In Chapter 7, we will examine the use of EAP and EAPOL in the context of IEEE 802.11 wireless LAN security. There is an increasing prominent trend in many organizations to move a substantial portion or even all information technology operations to an internet-connected infrastructure known as enterprise cloud computing. This section provides an overview of cloud computing. NIST defines cloud computing as a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources. For example, networks, servers, storage, applications, services that can be rapidly provisioned and released with minimal management effort or service provider information. This cloud model promotes availability and is composed of 5 essential characteristics, 3 service models, and 4 deployment models. The definition refers to various models and characteristics whose relationship is illustrated in the figure. The essential characteristics of cloud computing include the following. Broad network access. Capabilities are available over the network and accessed through standard mechanisms that promote use by heterogeneous thin or thick client platforms, for example, mobile phones, laptops, and PDAs, as well as other traditional or cloud-based software services. Rapid elasticity. Cloud computing gives you the ability to expand and reduce resources according to your specific service requirement. For example, you may need a large number of server resources for the duration of a specific task. You can then release these resources upon completion of the task. Measured service. Cloud systems automatically control and optimize resource use by leveraging a metering capability at some level of abstraction appropriate to the type of resource. For example, for storage, processing, bandwidth, and active user accounts. Resource usage can then be monitored, controlled, and reported, providing transparency for both the provider and consumer of the utilized service. On-demand self-service. A consumer can unilaterally provision computing capabilities such as server time and network storage as needed automatically without requiring human interaction with each service provider. Because the service is on demand, the resources are not permanent parts of your IT infrastructure. Resource pooling. The provider's computing resources are pooled to serve multiple consumers using a multi-tenant model with different physical and virtual resources dynamically assigned and reassigned according to consumer demand. There is a degree of location independence in that consumer generally has no control or knowledge of the exact location of the provided resources, but may be able to specify location at a higher level of abstraction, for example, country, state, or data center. Examples of resources include storage, processing, memory, network bandwidth, and virtual machines. Even private clouds tend to pool resources between different parts of the same organization. NIST defines 3 service models, which can be viewed as nested service alternatives. Software as a Service, SAAS. The capability provided to the consumer is to use the provider's applications running on a cloud infrastructure. The applications are accessible from various client devices through a thin client interface such as a web browser. Instead of obtaining desktop and server licenses for software products it uses, an enterprise obtains the same functions from the cloud service. SAAS saves the complexity of software installation, maintenance, upgrades, and patches. Examples of services at this level are Gmail, for Google's email service, and Salesforce.com, which helps firms keep track of their customers. Platform as a Service, PaaS. The capability provided to the consumer is to deploy onto the cloud infrastructure consumer-created or acquired applications created using programming languages and tools supported by the provider. PaaS often provides middleware-style services such as database and component services for use by applications. In effect, PaaS is an operating system in the cloud. Infrastructure as a service, IaaS. The capability provided to the consumer is to provision processing, storage, networks, and other fundamental computing resources, where the consumer is able to deploy and run arbitrary software, which can include operating systems and applications. IaaS enables customers to combine basic computing services, such as number crunching and data storage, to build highly adaptable computer systems. NIST defines 4 deployment models. Public cloud. The cloud infrastructure is made available to the general public or a large industry group and is owned by an organization selling cloud services. The cloud provider is responsible for both the cloud infrastructure and for the control of data and operations within the cloud. Private cloud. The cloud infrastructure is operated solely for an organization. It may be managed by the organization or a third party and may exist on-premise or off-premise. The cloud provider is responsible only for the infrastructure and not for the control. Community cloud. The cloud infrastructure is shared by several organizations and supports a specific community that has shared concerns. For example, mission, security requirements, policy, and compliance considerations. It may be managed by the organizations or a third party and may exist on-premise or off-premise. Hybrid cloud. The cloud infrastructure is a composition of 2 or more clouds, private, community, or public, that remain unique entities but are bound together by standardized or proprietary technology that enables data and application portability. For example, cloud bursting for local balancing between clouds. This figure illustrates the typical cloud service context. An enterprise maintains workstations within an enterprise LAN or set of LANs, which are connected by a router through a network or the internet to the cloud service provider. The cloud service provider maintains a massive collection of servers which it manages with a variety of network management, redundancy, and security tools. In the figure, the cloud infrastructure is shown as a collection of blade servers, which is a common architecture. Cloud Computing Reference Architecture, which is defined by NIST SP 500-292. It establishes a reference architecture described as follows. The NIST Cloud Computing Reference Architecture focuses on the requirements of what cloud services provide, not a how-to design solution and implementation. The reference architecture is intended to facilitate the understanding of the operational complexities in cloud computing. It does not represent the system architecture of a specific cloud computing system. Instead, it is a tool for describing, discussing, and developing a system-specific architecture using a common framework of reference. NIST developed the reference architecture with the following objectives in mind: to illustrate and understand the various cloud services in the context of an overall cloud computing conceptual model, to provide a technical reference for consumers to understand, discuss, categorize, and compare cloud services, to facilitate the analysis of candidate standards for security, interoperability, and portability, and reference implementations. The reference architecture depicted in the figure defines 5 major actors in terms of the roles and responsibilities. Cloud consumer, a person or organization that maintains a business relationship with and uses services from cloud providers. Cloud provider, a person, organization, or entity responsible for making a service available to interested parties. Cloud auditor, a party that can conduct independent assessment of cloud services, information system operations, performance, and security of the cloud implementation. Cloud broker, an entity that manages the use, performance, and delivery of cloud services and negotiates relationships between CPs and cloud consumers. Cloud carrier, an intermediary that provides connectivity and transport of cloud services from CPs to cloud consumers. The roles of the cloud consumer and provider have already been discussed. To summarize, a cloud provider can provide one or more of the cloud services to meet IT and business requirements of cloud consumers. For each of the three service models, SAAS, PAAS, IAAS, the CP provides the storage and processing facilities needed to support that service model, together with a cloud interface for cloud service consumers. For SAAS, the CP deploys, configures, maintains, and updates the operation of the software applications on a cloud infrastructure so that the services are provisioned at the expected service levels to cloud consumers. The consumers of SAAS can be organizations that provide their members with access to software applications and users who are directly using software applications, or software application administrators who configure applications for end users. For PAAS, the CP manages the computing infrastructure for the platform and runs the cloud software that provides the components of the platform, such as runtime software execution stack, databases, and other middleware components. Cloud consumers of PAAS can employ the tools and execution resources provided by CPs to develop, test, deploy, and manage the applications hosted in a cloud environment. For IaaS, the CP acquires the physical computing resources underlying the service, including the servers, networks, storage, and hosting infrastructure. The IaaS cloud consumer, in turn, uses these computing resources, such as a virtual computer, for their fundamental computing needs. The cloud carrier is a networking facility that provides connectivity and transport of cloud services between cloud consumers and CPs. Typically, a CP will set up service level agreements, SLAs, with the cloud carrier to provide services consistent with the level of SLAs offered to cloud customers, and may require the cloud carrier to provide dedicated and secure connections between cloud consumers and CPs. A cloud broker is useful when cloud services are too complex for a cloud consumer to easily manage. Three areas of support can be offered by a cloud broker. Service intermediation. These are value-added services such as identity management, performance reporting, and enhanced security. Service aggregation. The broker combines multiple cloud services to meet consumer needs not specifically addressed by a single CP, or to optimize performance or minimize cost. Service arbitrage. This is similar to service aggregation, except that the services being aggregated are not fixed. Service arbitrage means a broker has the flexibility to choose services from multiple agencies. The cloud broker, for example, can use a credit scoring service to measure and select an agency with the best score. A cloud auditor can evaluate the services provided by a CP in terms of security controls, privacy impact, performance, and so on. The auditor is an independent entity that can assure that the CP conforms to a set of standards. In general terms, security controls in cloud computing are similar to the security controls in any IT environment. However, because of the operational models and technologies used to enable cloud service, cloud computing may present risks that are specific to the cloud environment. The essential concept in this regard is that the enterprise loses a substantial amount of control over resources, services, and applications, but must maintain accountability for security and privacy policies. The Cloud Security Alliance lists the following as the top cloud-specific security threats, together with suggested countermeasures. Abuse and nefarious use of cloud computing. For many CPs, it is relatively easy to register and begin using cloud services, some even offering free limited trial periods. This enables attackers to get inside the cloud to conduct various attacks, such as spamming, malicious code attacks, and denial of service. PAAS providers have traditionally suffered most from this kind of attack. However, recent evidence shows that hackers have begun to target IaaS vendors as well. The burden is on the CP to protect against such attacks, but cloud service clients must monitor activity with respect to their data and resources to detect any malicious behavior. Countermeasures include 1. Stricter initial registration and validation processing. 2. Enhanced credit card fraud monitoring and coordination. 3. Comprehensive introspection of customer network traffic. And 4. Monitoring public blacklists for one's own network blocks. Malicious insiders. Under the cloud computing paradigm, an organization relinquishes direct control over many aspects of security and, in doing so, confers an unprecedented level of trust onto the CP. One grave concern is the risk of malicious insider activity. Cloud architectures necessitate certain roles that are extremely high risk. Examples include CP system administrators and managed security service providers. Countermeasures include the following. 1. Enforce strict supply chain management and conduct a comprehensive supplier assessment. 2. Specify human resource requirements as part of legal contract. 3. Require transparency into overall information security and management practices as well as compliance reporting. And 4. Determine security breach notification processes. Risks and countermeasures. Continued. Insecure interfaces and APIs. CPs expose a set of software interfaces, or APIs, that customers use to manage and interact with cloud services. The security and availability of general cloud services are dependent upon the security of these basic APIs. From authentication and access control to encryption and activity monitoring, these interfaces must be designed to protect against both accidental and malicious attempts to circumvent policy. Countermeasures include 1. Analyzing the security model of CP interfaces. 2. Ensuring that strong authentication and access controls are implemented in concert with encrypted transmission. And 3. Understanding the dependency chain associated with the API. Shared technology issues. IaaS vendors deliver their services in a scalable way by sharing infrastructure. Often, The underlying components that make up this infrastructure, CPU caches, GPUs, etc., were not designed to offer strong isolation properties for a multi-tenant architecture. CPs typically approach this risk by the use of isolated virtual machines for individual clients. This approach is still vulnerable to attack by both insiders and outsiders, and so can only be part of an overall security strategy. Countermeasures include the following. 1. Implement security best practices for installation configuration. 2. Monitor environment for unauthorized changes activity. 3. Promote strong authentication and access control for administrative access and operations. 4. Enforce SLAs for patching and vulnerability remediation. And 5. Conduct vulnerability scanning and configuration audits. Data loss or leakage. For many clients, the most devastating impact from a security breach is the loss or leakage of data. We address this issue in the next subsection. Countermeasures include the following. 1. Implement strong API access control. 2. Encrypt and protect integrity of data in transit. 3. Analyze data protection at both design and runtime. And 4. Implement strong key generation, storage and management, and destruction practices. Risks and countermeasures continued. Account or service hijacking, usually with stolen credentials, remains a top threat. With stolen credentials, attackers can access critical areas of deployed cloud computing services, allowing them to compromise the confidentiality, integrity, and availability of those services. Countermeasures include the following. 1. Prohibit the sharing of account credentials between users and services. 2. Leverage strong two-factor authentication techniques where possible. 3. Employ proactive monitoring to detect unauthorized activity. And 4. Understand CP security policies and SLAs. Unknown risk profile. In using cloud infrastructures, the client necessarily cedes control to the CP on a number of issues that may affect security. Thus, the client must pay attention to and clearly define the roles and responsibilities involved for managing risks. For example, employees may deploy applications and data resources at the CP without observing the normal policies and procedures for privacy, security, and oversight. Countermeasures include 1. Disclosure of applicable logs and data. 2. Partial full disclosure of infrastructure details, for example, patch levels and firewalls. And 3. Monitoring and alerting on necessary information. Similar lists have been developed by the European Network and Information Security Agency and NIST. NIST guidelines on security and privacy issues and recommendations. As can be seen from the previous section, there are numerous aspects to cloud security and numerous approaches to providing cloud security measures. A further example is seen in the NIST guidelines for cloud security, specified in SP 814 and listed in the table. Thus, the topic of cloud security is well beyond the scope of this chapter. In this chapter, we focus on one specific element of cloud security. And this is page 2 of 2. Take a moment and review the slide. Thank you. Data protection in the cloud. There are many ways to compromise data. Deletion or alteration of records without a backup of the original content is an obvious example. Unlinking a record from a larger context may render it unrecoverable, as can storage on an unreliable media. Loss of an encoding key may result in effective destruction. Finally, unauthorized parties must be prevented from gaining access to sensitive data. The threat of data compromise increases in the cloud due to the number of and interactions between risks and challenges that are either unique to the cloud or more dangerous because of the architectural or operational characteristics of the cloud environment. Database environments used in the cloud computing can vary significantly. Some providers support a multi-instance model, which provides a unique DBMS running on a virtual machine instance for each cloud subscriber. This gives the subscriber complete control over role definition, user authentication, and other administrative tasks related to security. Other providers support a multi-tenant model, which provides a predefined environment for the cloud subscriber that is shared with other tenants, typically through tagging data or with a subscriber identifier. Tagging gives the appearance of exclusive use of the instance, but relies on the CP to establish and maintain a sound, secure database environment. Data protection in the cloud. Data must be secured while at rest, in transit, and in use, and access to the data must be controlled. The client can employ encryption to protect data in transit, though this involves key management responsibilities for the CP. The client can enforce access control techniques, but again, the CP is involved to some extent depending on the service model used. For data at rest, the ideal security measure is for the client to encrypt the database and only store encrypted data in the cloud, with the CP having no access to the encryption key. So long as the key remains secure, the CP has no ability to read the data, although corruption and other denial of service attacks remain a risk. A straightforward solution to the security problem in this context is to encrypt the database and not provide the encryption-decryption keys to the service provider. This solution by itself is inflexible. The user has little ability to access individual data items based on searches or indexing on the key parameters, but rather would have to download entire tables from the database, decrypt the tables, and work with the results. To provide more flexibility, it must be possible to work with the database in its encrypted form. There are various examples of such an approach as shown in the figure, which have been reported on, both in practice and in academia. There's 4 entities involved. The data owner, an organization that produces data to be made available for controlled release either within the organization or to external users. User, human entity that presents requests, queries to the system. The user could be an employee of the organization who is granted access to the database via the server, or a user external to the organization who, after authentication, is granted access. Client, front end that transforms user queries into queries on the encrypted data stored on the server. Server, an organization that receives the encrypted data from a data owner and makes them available for distribution to clients. The server could, in fact, be owned by the data owner, but more typically is a facility owned and maintained by an external provider. For our discussion, the server is a cloud server. Cloud Security as a Service, SECAAS, has generally meant a package of security services offered by a service provider that offloads much of the security responsibility from an enterprise to the security service provider. Among the services typically provided are authentication, antivirus, anti-malware, spyware, intrusion detection, and security event management. In the context of cloud computing, Cloud Security as a Service, designated as SECAAS, is a segment of the SEAAS offering of a CP. The Cloud Security Alliance defines SECAAS as the provision of security applications and services via the cloud, either to cloud-based infrastructure and software or from the cloud to the customer's on-premise systems. The Cloud Security Alliance has identified the following SECAAS categories of service: identity and access management, data loss prevention, web security, email security, security assessments, intrusion management, security information and event management, encryption, business continuity and disaster recovery, and finally, network security. In this section, we examine these categories with a focus on security of the cloud-based infrastructure and services. Identity and access management, IAM, includes people, processes, and systems that are used to manage access to enterprise resources by assuring that the identity of an entity is verified, and then granting the correct level of access based on this assured identity. One aspect of identity management is identity provisioning, which has to do with providing access to identified users and subsequently deprovisioning or deny access to users when the client enterprise designates such users as no longer having access to enterprise resources in the cloud. Another aspect of identity management is for the cloud to participate in the federated identity management scheme, as in Chapter 4, used by the client enterprise. Among other requirements, the cloud service provider, CSP, must be able to exchange identity attributes with the enterprise's chosen identity provider. The access management portion of IAM involves authentication and access control services. For example, the CSP must be able to authenticate users in a trustworthy manner. The access control requirements in SPI environments include establishing trusted user profile and policy information, using it to control access within the cloud service, and doing this in an audible way. Data loss protection, DLP, is the monitoring, protection, and verification of security when data is at rest, in motion, and in use. Much of DLP can be implemented by the cloud client, such as discussed in section 5.6. The CSP can also provide DLP services, such as implementing rules about what functions can be performed on data in various contexts. Web security is a real-time protection offered either on-premise, through software appliance installation, or via the cloud by proxying or redirecting web traffic to the CP. This provides an added layer of protection on top of things like antiviruses to prevent malware from entering the enterprise via activities such as web browsing. In addition to protecting against malware, a cloud-based web security service might include usage policy enforcement, data backup, traffic control, and web access control. A CSP may provide a web-based email service for which security measures are needed. Email security provides control over inbound and outbound email, protecting the organization from phishing, malicious attachments, enforcing corporate policies such as acceptable use, and spam prevention. The CSP may also incorporate digital signatures on all email clients and provide optional email encryption. Security assessments are third-party audits of cloud services. While this service is outside the province of the CSP can provide tools and access points to facilitate various assessment activities. Intrusion management encompasses intrusion detection, prevention, and response. The core of this service is the implementation of intrusion detection systems and intrusion prevention systems at entry points to the cloud and on servers in the cloud. An intrusion detection system is a set of automated tools designed to detect unauthorized access to a host system. We discussed this in Chapter 1. An intrusion prevention system incorporates an intrusion detection system functionality, but also includes mechanisms designed to block traffic from intruders. Security Information and Event Management, CIEM, aggregates via push or pull mechanisms, log and event data from virtual and real networks, applications, and systems. This information is then correlated and analyzed to provide real-time reporting and alerting on information events that may require intervention or other types of response. The CSP typically provides an integrated service that can put together information from a variety of services and sources, both within the cloud and within the client enterprise network. Encryption is a pervasive service that can be provided with data at rest in the cloud, email traffic, client-specific network management information, and identity information. Encryption services provided by the CSP involve a range of complex issues, including key management, how to implement virtual private networks, VPNs, services in the cloud, application encryption, and data content access. Business continuity and disaster recovery comprise measures and mechanisms to ensure operational resiliency in the event of any service interruption. This is an area where the CSP, because of economies of scale, can offer obvious benefits to a cloud service client. The cloud service provider can provide backup at multiple locations with reliable failover and disaster recovery facilities. This service must include a flexible infrastructure, redundancy of functions and hardware, monitored operations, geographically distributed data centers, and network survivability. Network security consists of security services that allocate access, distribute, monitor, and protect the underlying resource services. Services include perimeter and server firewalls and denial of service protection. Many of the other services listed in this section, including intrusion management, identity and access management, data loss protection, and web security, also contribute to the network security service. Control functions and classes. Numerous documents have been developed to guide businesses thinking about the security issues associated with cloud computing. In addition to SP 800-144, which provides overall guidance, NIST has issued SP 800-146 Cloud Computing Synopsis and Recommendations. NIST's recommendations systematically consider each of the major type of cloud services consumed by businesses, including software as a service, infrastructure as a service, and platform as a service. While security issues vary somewhat depending on the type of cloud service, there are multiple NIST recommendations that are independent of the service type. Not surprisingly, NIST recommends selecting cloud providers that support strong encryption, have appropriate redundancy mechanisms in place, employ authentication mechanisms, and offer subscribers sufficient visibility about mechanisms used to protect subscribers from other subscribers and the provider. It also lists the overall security controls that are relevant in a cloud computing environment and that must be assigned to the different cloud actors. These are shown in the table. As more businesses incorporate cloud services into their enterprise network infrastructures, cloud computing security will persist as an important issue. Examples of cloud computing security failures have the potential to have a chilling effect on business interest in cloud services. And this is inspiring service providers to be serious about incorporating security mechanisms that will allow the concerns to be overridden by the potential subscribers. Some service providers have moved their operations to Tier 4 data centers to address user concerns about availability and redundancy. Because so many businesses remain reluctant to embrace cloud computing in a big way, cloud service providers will have to continue to work hard to convince potential customers that computing support for core businesses and processes and mission-critical applications can be moved safely and securely to the cloud. And to summarize, we've covered network access control, flexible authentication, cloud security as a service. We talked about the IEEE 802.1x port-based network access control and the cloud computing and related risks and countermeasures and data protection in the cloud and addressing cloud computing security. Okay, thank you for listening. Bye for now.